and creation all the way through analysis and some map making. So just to introduce myself a little further and what I do at Blue Marble, my name is Mackenzie. I'm a technical content writer, and I work with a few of our different teams and our customers to help provide resources and make sure that our customers are using the programs, to their full capabilities. Here at Blue Marble, we really are focused on creating programs that work well for our customers. About Blue Marble in general, as I said, we're focused on that user-driven development. We want to make programs that work for the people who use them. And our main two programs that we have are Geographic Calculator, an industry standard for coordinate system transformation and advanced coordinate system management. And then Global Mapper and Global Mapper Pro, sort of in tandem, a great GIS solution that we'll be exploring further today. A bit more about Global Mapper Pro and the program capabilities. First off, it's a really versatile and interoperable program. We support over 300 file formats in Global Mapper Pro. So any data that you have, you're likely able to load it into Global Mapper to visualize and further analyze the data. Same with exporting, hundreds of formats supported. So it's a great data conversion tool at, its basic level. Going further than that, there's great vector data and raster data imagery and such analysis tools, as well as data creation. We support LiDAR processing and that point cloud classification, rectification, and analysis, as well as some point cloud creation tools using drone or UAV collected images with the pixels to points tool. Transforming that point cloud or LiDAR data into a terrain grid, an elevation model is also a common workflow in Global Mapper Pro, creating that raster surface for further analysis, automatic break line extraction, contour generation, and even some volumetric terrain editing and volume calculations. Global Mapper has great tools for visualization, as well as some workflow optimization methods, including scripting. A new addition to the Global Mapper Pro program is the integration of the Python programming language. So if you're a Python developer, if you're currently using Python to automate some tasks, some workflow steps in other programs, and you want to throw some Global Mapper tools into that mix, start using those in your Python automation, you can absolutely do that with Global Mapper Pro. So in a minute, I'm going to step out of PowerPoint and into Global Mapper, and we'll take a look at some data processing. We'll go through some workflow steps to see, what Global Mapper really looks like and fully introduce it. A quick rundown of what we will be going over today. We're going to start with some data visualization. So I'll bring up a workspace with data loaded in. We'll look at some different ways to explore this particular data set in 2D and in 3D. We'll then move into some LiDAR data analysis, stick with some pretty basic analysis for ground classification in a point cloud, and mention a few other analysis tools along the way. We'll then take our point cloud data and convert it into an elevation grid. So we can create a raster surface modeling the terrain from that point cloud data. We'll talk about the digitizer tool and vector feature creation. So adding more data to our workspace, creating some features in Global Mapper. And then move into some terrain analysis. So going back to that created terrain grid, that surface model, and doing some volume calculations and some comparisons there. So with that, I'm going to jump out of PowerPoint and bring up Global Mapper. This is the Global Mapper interface for those of you who may not be familiar with it. Up at the top, we have some menus accessing, different functions and tools in the program. Below that are toolbars. Each of these buttons accesses a key function in the program, and these are customizable. You can move them, reorder them, hide them to customize the interface for your work. On the left here, we have the control center where we have the list of loaded data layers. Currently, we have one data layer loaded into this workspace. It is a point cloud LiDAR layer. And it looks like imagery displayed in our main data view right now because it's being colored with the RGB or elevation values in this case. We can change that visualization of the data just in this top-down view to start with our color LiDAR by or our LiDAR draw mode option, we can change this to view the point cloud by elevation. This is a great visualization. So we start to get to know the terrain in this area. We see the low spots and the high spots as colored and described by our default Atlas shader. And we have our legend displayed here as well. So we get a full picture of the elevation in this area. But LiDAR points don't just have that Z elevation often, they have additional information associated, and we can color the LiDAR here by any of those characteristics. So we can show our intensity values for this point cloud. Here we're looking at the bright high intensity values. That's a bare earth area. Those are our current project sites, and we can see those clearly depicted by intensity here. We can also view by things like point density. So the local point density within this point cloud to get a sense of how dense this point cloud is, whether there are some spots where more points are present per square meter. We can see here a channel cutting through our point cloud tile. It looks probably like the overlap between two flights for data collection. One very useful visualization option or draw mode for our point cloud is by classification. Here I have switched our draw mode to classification, and we're seeing a big gray square. This is an unclassified point cloud to start. These are all unclassified points, and we will add a little more meaning and some classification to some of these points in a moment. Before we jump into that more analysis method, I'm going to return our draw mode to elevation, and we can take a look at this data in the 3D viewer. So LiDAR is 3D, it has that elevation value, so it only makes sense to explore this data in 3D as well. Looking over the terrain here, we can move and toggle the data around to get different views on it, explore different aspects. We can see the elevation change as we dive into a pit sort of on the edge of our data here. And looking across the terrain, sort of placing ourselves on the ground as the viewer and looking across, we see that this is a relatively flat region. There's not too much elevation change going on here. Another tool to show the elevation change in a point cloud and see the 3D nature of this data is the path profile tool. And this creates a cross-sectional view of our point cloud or any 3D data. I'm going to go along and just left click and right click to draw a quick path profile across the edge of one of these pit features, and we can see that change in elevation. Our point cloud is still visualized with our elevation shader, and we can even take measurements in this view here, maybe get an average slope for the edge of this pit wall. So I mentioned classification, and we're going to jump into that. I'll change my visualization here back to classification. So we have all our unclassified points showing. And in Global Mapper, we can grab the digitizer tool to manually select and edit any points. With a swath of points selected here, we can use a manual classification button to assign a class to all of the selected points. But a better, maybe more intelligent way to go about classifying ground in this case is an automated classification method in Global Mapper Pro. So I'm going to deselect any points here and open my automatic ground classification tool from our automated analysis toolbar. And here we're classifying the one point cloud layer we have loaded. And Global Mapper is asking us for some parameters to help guide the program in order to find that more continuous ground surface and classify our points accurately. The first parameter is the local bin size. So what sort of ground size are we looking at to determine local variations in the elevation values as we look for that continuous ground surface? And below that are some parameters that help guide Global Mapper in what the expected terrain is in this area. So overall elevation change, the average or expected slope, and then a maximum building width parameter. This last parameter is a little more useful in more urban areas where you've got large flat topped buildings that you want the program to be aware of. Clicking OK to execute this classification, Global Mapper is going to go through and filter out the non-ground points in order to identify and classify our ground points. This is a point cloud that's about 6 million points, and it processes pretty quickly, sort of an average size point cloud tile here. And when that completes, we see two colors now represented in our point cloud classification draw mode. We've got all these brown points are ground. We can take a look at this in the 3D view again and bring us down sort of to the ground again. Looking across the terrain, we see that all of the features and structures sitting on top of the ground that are each represented by a handful of points, those are remaining with that gray color in this draw mode. They're still unclassified, but below that we have a fairly continuous ground classified area of points. Now that we've added this ground classification, we're more ready and equipped to make a digital terrain model. Closing the 3D view and opening our grid creation tool, we have the option to name the layer that we're going to create. This will create a new layer in the workspace, and we have options to choose how we want to go about gridding this data. So there's the classic tin method, of course, that's included in Global Mapper here, which will connect all of the points into a vector network of triangles. Note that with this tin method, Global Mapper will by default interpolate over those vector triangles to create a raster elevation surface, but you do have the option to save the triangulation network as a vector layer, export it to a vector format if that is an output that you're interested in creating from some data. We are going to choose a different grid method. I'll just select a binning method since we do have a fair number of points here. The binning method will spatially bin the points, and then with the minimum value option, choose the lowest point from each of those spatial bins in order to best represent our ground surface. We'll let Global Mapper determine the automatic spacing based on the local point spacing. And then this tight loose slider determines how far across gaps in our data Global Mapper will interpolate. As a last step, I do want to filter our LiDAR points. Since we're using a point cloud here, I can filter the points by classification that we just applied to only use our ground classified points. And this just, ups the accuracy, make sure that we're using those verified ground points in order to create this terrain model that we're interested in. Clicking OK, Global Mapper adds that new layer to the workspace. And here we have it. It is colored by elevation, since it is an elevation grid, and this is a 3D layer as well. So we can open it in the 3D view, see that ground terrain here, and again, use the path profile view as well to view the a cross section of this grid. So now that we have this terrain grid, we can take a closer look at some sections of it. These bare earth project sites that we mentioned we saw in the RGB visualization of the point cloud and the intensity visualization, they're fairly flat areas. And in this scenario, we want to create a new project site. We have a proposed project site going into this area. So to start off, we want to create some sort of vector shape outlining that area, telling us that this is where our proposed project site is. Now we can grab the digitizer tool in Global Mapper for data selection and editing and creation. And we can absolutely go ahead and manually draw some shapes onto our map. Freeform polygons, rectangles, lines, and even using a coordinate geometry tool to make some more precise lines and features. But I'm going to take a different approach and move to the digitizer menu. Here, I'm going to go into advanced feature creation options, and down at the bottom, we have this option to insert a pad site from a library. So you'll see that many options in this menu are grayed out. They're not able to be selected because they rely on existing feature selection, more for editing. But we can choose to insert the pad site from a library, and nothing changes until I click at a point on the map. This prompts me to select the pad site feature template. So here, Global Mapper has two built-in feature templates. And these are just constellations of vector features that exist in a file that I've loaded into Global Mapper and told it to remember. It makes it really easy to place specific sized features down on the map at any given spot. You don't have to use just these two built-in options. There is an option down the bottom of this dialog to add a template from a file. And this allows you to pick any vector data file that will be loaded into Global Mapper and remembered by Global Mapper. So this is different than just loading a new data layer into the program because it's not tied to the coordinate location where the data layer says that feature should be. This is just taking the structure, the shape of the features, and allowing you, the user, to place them anywhere on the map as you see fit. I'll go ahead and use one of our built-in options for our 3-well exhibit pad. We can alter the insertion point or that center point that I clicked on the map if you want to use some specific or exact coordinates. And with that template selected, click OK, and we see vector features have been added to our map here. So these are now vector features. We can go ahead, we can alter the shape, we can add more vector features. They are contained in their own layer in the control center here, and we can toggle that on and off to show and hide them. And so we have our proposed project site sort of defined spatially. Next, I can take the path profile tool once again, and we note that existing project sites are flattened. So for this new project site, we're probably going to need to alter the terrain and flatten out this area. Drawing a quick path profile across this proposed site, we see that the terrain is indeed rough, and we will need to flatten it to some extent. We'll flatten it to an elevation of about 1,059 meters. That seems about in the middle of our range here. And drawing multiple path profiles, we can see, the roughness throughout this area. Now to flatten this site, there are a few different methods that we can employ. I'm going to start by selecting this largest area feature, the bounds for this new site. And I can create a new small tile of an elevation grid with the grid creation tool if this feature has a specific elevation. I can also use a digitizer advanced feature creation option to calculate a flattened site plan. This allows me to enter a specific elevation to flatten the height to a fixed elevation. It also gives me the option to calculate a break-even height and flatten to that elevation. So calculate the flattened height that equalizes the cut and the fill volume. So the least amount of earth would need to be, removed from the site. It's more of a reorganization in this case. I'm actually going to, avoid this method for now, and we're going to do some direct terrain editing on this generated grid. And we're going to do that with the terrain painting tool. This is a tool that allows you to manually manipulate and reshape the grid that you have loaded into Global Mapper. There's a bunch of different operations to choose from. You can fill in holes if your data has some gaps in it with some interpolation methods. You can smooth the terrain based on a local average, raise or lower the terrain by a discrete height, or slope the terrain along a line, maybe to grade a road, slope the terrain across a line to cut a ditch or add a levee to an area, create holes in your data, or we're going to choose this middle option to set the terrain height. So for a specific area, we want to set the terrain height to something even and flat. We'll move over to the other side of this little dialog to choose the brush type. We can choose a few different ones, a point, so just within a specific point. We can use a line mode and just, scribble an area on the terrain, and we've just cut a ditch into this grid at a specific height of 10 meters here. I'll just use the undo button to reverse that change. We can manually draw an area, maybe tracing our project site, or we can choose to paint the selected feature. Since we have that feature existing in the workspace, this is the easiest option for us. We'll alter our units to meters here and set our height to that 1,059 meters. and set the feathering distance to 10 meters. This feathering distance is how far from the edge of our selected area Global Mapper will use to blend the altered, the flattened terrain into the original elevation values so that we have a smoother transition and not such a harsh vertical wall in areas where the elevation differs. With these options set up, I'll paint the selected features, and immediately Global Mapper flattens this area. Closing the terrain painting tool and clearing my feature selection, we see again this is a flattened area, and we can explore that further in the 3D view or with this cross profile. We have our feathered or sloped edges, our flattened site plan, and a slope on the other side as well. Now we've altered this terrain, we've mocked up this flattened site for our new project, but we don't actually have any numbers associated with this. We didn't get any volume calculation from that terrain painting method. So we want to compare this edited terrain with the original terrain derived by LiDAR. Since we edited this layer and we only have this one elevation grid layer loaded in the workspace, I'm going to quickly change the description to note that this is an edited DTM layer. And we can create the original terrain again by bringing back our point cloud quickly and using the grid create tool to just duplicate that original DTM layer. Using the same method, being sure to filter our points, same spacing and settings all throughout the dialog. Global Mapper creates this layer again, and displaying both of these, we can see that the only difference between them, since they were created with the same source data and the same method, is the flattened site plan, that manual editing that was done. So we can easily calculate a volume now. From the analysis menu, we'll measure the volume between our two surfaces in this workspace here, subtracting our edited terrain from the original. And we'll set the bounds for this operation just to the data on screen. We know that nothing beyond this has been edited. This gives us a calculation, gives us some numbers in cubic meters in this case for the cut volume or volume of earth that would need to be removed in order to create this flattened site, and the fill volume, the amount of volume that would need to be brought in or redistributed to fill the to create the flattened site. This operation to calculate volume did not create a new layer in Global Mapper, but it did give us these numbers that can easily be copied and pasted into a report, into some notes to go along with the data that we're creating here. So we have those general volume measurements, and we can see with the image swipe tool how the terrain has changed. We can also use the path profile tool, again, a very useful tool I keep coming back to show both of these layers and the elevation difference between them. The filled layer that is more jagged at the top with our red line is that unedited DTM layer. The blue line we see flattened, that is our edited, our terrain painted proposed project site layer. So we can see just along this single profile I drew where terrain would need to be added and where it would need to be taken away. To better visualize this for the entire area and not this one discrete line, we can use another calculation that applies a subtraction on a pixel by pixel basis to compare the two loaded terrain layers. From the analysis toolbar, we will use a signed subtraction method to create this difference grid, because we are calculating the difference between the original and the edited terrain layer. We'll want to choose the edited and original terrain layer as our layers to use in this calculation. And I'm going to choose to apply a specific shader to be used for this layer because we're not modeling elevation with the layer that is going to be created here. We're modeling the difference or the change between two existing terrain grids. Again, I'm just going to truncate the bounds to the visible data, and Global Mapper generates our new layer. Now, this is the change shader that I chose to apply. We see the white areas here are areas where there's no change. So anywhere else besides the area we explicitly edited with the terrain painting tool. And within this edited area, we can see the red, the positive values where Earth would need to be added in order to create this flattened site. And then the blue areas where Earth would need to be taken away. Turning off the underlying terrain layers, this is a gridded layer, although not showing, terrain or elevation in the classic way. Each pixel does contain an elevation or difference value. And that means we can use the path profile tool to view it. And along this cross section that I drew, we have areas where Earth would need to be taken away. And the area from 0 to this surface is the amount at that particular coordinate location. And then area where Earth would needed to be added or filled in. So that shows us where those cut and fill volumes that were calculated, where they're going to be distributed, and how they really impact the terrain area. And this is a great visual representation of that predicted change as we go to, implement this new project. So here we started with just one layer in this workspace, the point cloud layer. And we have taken it all the way from an unclassified point cloud layer to some terrain grids, added some vector features, edited that terrain, and even done a difference analysis to better prepare us to write this project proposal or go into the field and begin this implementation. So this is just one use case for Global Mapper with some, terrain editing. We didn't by any means get to all the tools that are available in the program, but it is extensive and it is great for this 3D data work, especially as 3D data is becoming more prominent and more accessible within all industries. So with that, I think we have some time for some questions, but I do want to thank everyone for being here today and attending this webinar. I hope that something with Global Mapper Pro piqued your interest. And if you do have any questions, ask them now, or you can reach out via email, find more information, and download a trial of the program for free on our website as well. So thank you.